Welcome to everybody. First of all, thank you very much for inviting me here today. It's an honor and an exciting challenge to have the opportunity to present this part of my research activity to you. My name is Avatara, and I'm the Virthulab voice. In this presentation, first I will provide a short tribute to the great scientists that allowed us to play with a game called Sociophysics. Then, giving an informal definition of complex system science, I'm going to explore the fundamental parallelism between particle systems, physical simulations, and psychological inspired agent-based modeling. After this first part, I'll provide a possible set of fundamental ingredients for sociophysics modeling, presenting 3 classical and widely adopted sociophysics models from literature. In the last part of the presentation, I will describe the development of a brand new framework to study opinion dynamics, consistent with the cognitive dissonance theory by Leon Thurston and the psychological field theory of Kurt Lewin. Finally, some numerical results will be presented and a psychological interpretation will be provided. Even if they don't look like superheroes, actually these 4 scientists, but more than many others, contributed to the birth of sociophysics. At the beginning of my personal modern history of sociophysics is this human being's. His name is John von Neumann, and among the other things, developed the general theory for the simulated annealing algorithm, as well as for the Monte Carlo methods, 2 fundamental family of statistical mechanics recipes, which allow to translate in computational terms very complex problems from different domains, directly simulating the system under scrutiny. Together with John von Neumann, Alan Turing contributed to the computer revolution. Moreover, from one side his job made the numerical simulations of particle systems imagined by his friend Janus possible, and from another side his conjectures about the parallelism between computer and human mind still represent a fundamental contribution to the philosophy of cognitive-inspired system development. Jumping forward in time, John Nash actually won the Nobel Prize in Economics, just because the category psychology didn't, as well as doesn't exist, but of course it would be more appropriate. Above all, he created either a theoretical framework providing the mathematics to thread complex social interactions dynamics, as well as a set of fundamental mathematical tools, such as the replicator equation, and the concept of equilibrium in single and repeated dynamics. In other words, Nash provided a new, and more effective, mathematical language to treat social dynamics. At the end of this brief history, I actually go back in time to the mind who, for the first time, provided a psychosocial theoretical framework to threat and handle complexity in social psychology. The first fundamental contribution of Kurt Lewin was his intuition of a common root of complexity, for individuals and groups, given by the complex dependence F, characterizing the relation between the behavior of a subject I, or a group I, at a certain time t+1, and the features characterizing the subject I at time t, and the environment J, at the same time t. The second fundamental contribution by Lewin is the concept of psychological field, which represents, using the words of Lewin, the result of the complex combination, so not just a sum, of the real structure of the group, in terms of communication potential, with every single psychological representation the group members have of network, group itself. Finally, Lewin saved us from the impossibility of understand psychosocial dynamics by means of laboratory experiments, describing the threshold between reductionism and effectiveness for the experimental and theoretical study of complex social dynamics by means of laboratory experiments, or numerical simulation I would say today. So studying macroscopic social dynamics, just observing small group dynamics, or computation simulation. So far we explored some building blocks of the sociophysics framework, but in order to go ahead, a definition of what a complex system is, and why the mathematics behind this concept is so important for the psychosocial modeling of sociophysics systems is required. To define a single complex system is very easy, as well as to provide a very general definition of this entity could remain elusive and challenging. A system where a large number of interacting dynamical elements, or processes, dominated by a set of interacting rules, even very simple rules, determine complicated and self-organized emergent phenomena. Many complex systems must be studied considering at least 3 different levels of description. The first ingredient is a good theoretical description of the inner mechanisms regulating the node's behavior, of course depending by the domain under scrutiny, and where good means here simple and clear in computational terms. The second ingredient is of course an effective description of the consequences of nodes' interactions, in terms of possible changes in the state of the nodes, and or of the system as a whole. And the last ingredient should be an appropriate description of the node's network, or of their space of possible interactions, in order to take into account the possible environmental constraints or external sources of influence of interest for the study. Once we have all the ingredients, we need a way to validate the model, or to improve it after some experimental feedback. So the rationale of numerical simulation is to connect the order parameter to a set of possible control parameters, inherently defined by the theoretical model, choosing what control parameters must be maintained as fixed, our constant, and what control parameters must be manipulated during the numerical simulation of the model as independent factors. Of course these choices are very important, and should be driven always by the theory, as well as by the Lewin's words. The control parameters could be related with the node's initial states, parameters or internal rules of behaviors. Others control parameters can be related with the rules determining nodes' interactions, or their consequences. Finally, some control parameters can be related with the network's topology, for instance varying the connectivity, or the connectivity dynamics. At the same time, the simulation of model produces natural observables that can be considered as order parameter of the system, and used to study the model as phenomenology. Through such variables usually a computational model is validated or rejected, by means of a direct comparison between the simulation results, and whenever is possible, the experimental observations. Among the others the order parameters can be related with different features of the node's dynamics, with statistics related with the encounters, or with the network's evolution. The sociophysics modeling actually represent a particular case of physical particle system simulation approach. Within this domain, usually a theoretical model drives the implementation of a computational engine designed to simulate a theoretically coherent scenario. The model usually requires the definition of some control parameters, for instance the node's initial position, the characteristics of the particle's interactions dynamics, and the so-called surrounding conditions. The numerical simulation of such systems allows the testing of the theoretical model implemented through a direct comparison between independent reference, or real data, with the order parameters dynamics. As I said before, agent-based modeling can be seen as a particular case of particle systems modeling. In the agent-based modeling usually the theoretical background is related with psychological, or psychosocial theories. For instance, in a very classical example of opinion dynamics modeling, the parallelism with the particle system modeling is pretty evident. Within this example the model's control parameters are the node's agent state at the beginning of the simulations, the rules determining the interaction dynamics with the contacts, and the contact network itself. In this case a simple rule for the agent's interaction implements the theory of social impact by Virthulab. Basically, the fundamental rule of the model is that at each time step every agent assumes the opinion of the majority of its neighbors, and in case of stalemates the old opinion is maintained. Different order parameters have been defined to study and validate the model. The success of complex system science is the possibility to explain emergent properties of interest of many physical systems, starting from the understanding of their microscopical dynamics. Such a success is ranging from matter physics, where for instance the simple and elegant Ising model is able to explain the ferromagnetic transitions, to the human crowd dynamics modeling, where is exploited the Boltzmann model of ideal gas. Such very elegant theoretical models are not describing the real and quantum nature of the processes under scrutiny, nevertheless they capture perfectly the average outcomes of real systems. Using the words of Lewin, we could say that in these two examples, all the fundamental ingredients of the real complexity characterizing these systems are captured by the theoretical models, and nothing else matters. The opinion dynamics modeling represent a challenging as well as classical example of sociophysics and ABM application field. The 90% of existing socio-physical frameworks to study such systems are characterized at least by 4 fundamental ingredients. These critical control parameters are the node state representation, in this case the opinion, the network topology, the encounter dynamics, and finally the evolution rules frequently related with the agent's interactions. Possible and frequently adopted framework evolution can include possible external fields affecting the nodes, simulating for instance propaganda or media dynamics. It is possible to introduce specific modeling elements to study the effects of group sizes on specific dynamics of interests, to take into considerations the complexity emerging from possible different timescales characterizing the coupled processes under simulation. Finally, the complexity of real systems is captured by means of coupling of different ingredient dynamics. So for instance the network topology could change depending on the node state, which at the same time can be effects along another timescale by the network topology itself to determine their states. A first example of Sociophysics ABM application to the opinion dynamics modeling is represented by the Ising-like model of opinion dynamics on regular square lattice. In this model, the fundamental requirements of the classical sociophysics framework are fulfilled, taking inspiration by a very elegant physics model describing the ferromagnetic dynamics of metals. The node state is represented by a binary opinion, randomly assigned at the beginning of the simulation. The network's topology is very simple, a square lattice, so that each agent has 4 neighbors, and an equal number of possible interactions with the world at each time step. Finally, the evolution rules simply implement a trivial approximation of the social impact theory by Bib-Latané. In particular, each agent, at each time step, assume the opinion which is proposed by the majority of its neighbors. A more refined model of opinion dynamics is a different and research model of bounded rationality. In this model of opinion dynamics, a full connected network is considered as characterizing the node's communication with a binary random encounters mechanism. This model represents the node state, the opinion, as a continuous variable ranging in the interval 0, 1. After the selection of the first agent I, the numerical recipe proposed by the model proceeds to the random extraction of another agents, here indicated as j at the time t of the event. We have a couple of agents, I and j, whose opinions are characterized by a certain distance along the opinion space, here indicated as delta Oij. The different model actually implemented as fundamental psychological mechanism and interaction threshold, corresponding to a sort of agent's open-mindedness, characterizing every agent and determining the encounter's outcomes. In particular, the encounter's effect changed whenever the distance between the opinion of I and j, here delta Oij, is greater or smaller than delta Oc. If delta Oij of time t is equal or smaller than delta Oc, the opinion of I and j at the time t and 1 will approach each other by a factor mu. Elsewhere, if Oij at time t is greater than delta Oc, the opinions of I and j remain the same. Beyond the rich phenomenology characterizing the different model, the most important insights, as well as validable outcomes of the model, are related with the dynamics of the community fragmentation at the equilibrium. In particular, from the numerical simulation of the model it emerges a clear relation between the final fragmentation of the system and the opinion threshold delta Oc. When delta Oc is large, a single opinion cluster emerges at the equilibrium. Whenever delta Oc is decreased, different equilibria present more fragmented scenarios. A fundamental results from the different and research model is the numerical approximation of the law linking the number of opinion clusters at the equilibrium with the node's average open-mindedness. One of the most interesting improvement of the different model, devoted to increase the psychological consistency of the framework, is that proposed by Novak and colleagues, implementing a coupling between agents labeled as affinity, mediating the consequences of the agent's encounters. Also in the Novak's model there is a continuous opinion space containing the opinion of a random extracted agent I, which is coupled with another randomly extracted agent j. Again, a possible approach to the agent's opinions is possible and determined by a convergence parameter mu. Nevertheless, in the Novak's model is introduced a control parameter to implement the functional synchronization theory, which claims that the degree of agreement or social influence effectiveness should be related with the strength of agent's relation. The model's equation determining the system dynamics encapsulated in the different model a relation between the interacting agents' reciprocal affinity and degree of opinion convergence determined by their encounters. In the last part of my talk, I would like to apply the building blocks described so far, in order to present the development of a new framework devoted to the study of opinion dynamics, with a self-consistent and dynamical modeling of affinity between agents. This brand new framework will integrate the different research model with the Novak model, and will try to go beyond the limitations of these models, introducing a self-consistent evolution of opinion and affinity between agents, and a more ecological representation of the social space and of the encounter's dynamics. In particular, the new framework updating will make it consistent with the Festianist cognitive dissonance theory, and with the Lewin psychological field theory. First of all, a brief reminder to the fundamental ingredients. In our framework, as in the different model, each agent I is characterized by a randomly extracted opinion within the interval 0, 1. A special ingredient of our model is represented by the affinity matrix, which reports the degree of affinity between each couple of agents. In our numerical approximation, the affinity parameter ranges between 0 and 1, and in the initial random affinity matrix, the element alpha ij, at time t, is not equal to the element alpha ji. At time t, another fundamental improvement proposed by our model is related with the network topology. As in the different model, we adopted a full connected network in order to better represent real humans communities. Nevertheless, even if each possible interaction between two randomly selected agents can happen, its probability is related to a parameter that we labeled social distance, d, characterizing every couple of agents I and j within the system. In particular, two agents will be closer within the social distance space if they would share similar opinions, and if they would have a large affinity to the others. Such linkage between the state space of the nodes, the opinion space, with the internal representation the nodes have each other, should improve the consistency of the framework with the Lewin psychological field theory. The next ingredient required by the recipe is the encounter dynamics. Also in this case, this framework provides a brand new mechanism with respect to the existing socio-physical models. In order to reduce the gap with the psychological internal coherence of the framework, the encounter dynamics is organized along 3 steps. In the first, defined organization step, a first agent I is randomly selected with a probability of 1 over n. At this time, a distance in opinion can be defined between the agents I and every other agent j, as well as distance in the affinity dimension. As a consequence, the random extraction of the first agent in some way organizes the psychological field to establish the subsequent encounter. The second step of the recipe for the encounter dynamics is the definition of the social distances space of the subject I, as the product of the absolute values of its distances to every other agents in the systems, with the results of 1 minus the affinity with them. This operation produces a one-dimensional space where the agent I represents a vertex, and all the other agents j scattered with the distance of dij finally. In order to increase the physical plausibility of the algorithm determining the agents' encounters, we consider that from one side real people don't meet each other randomly, but at the contrary frequently meet, for instance weekly to have a beer, very friends of them, sharing their same opinions and characterized by good affinities with and from them. At the same time, depending on the environment constraints, rare encounters can and should be possible. In order to accomplish this task, the step 3 starts considering the social distances space of the subject I. Then it applies a physical white thermalization to the system, namely adding a Gaussian distributed perturbation of nodes' positions, with average value of 0, and a standard deviation equal to kt. Finally, after the thermalization phase, the final step of the recipe is the selection of the nearest agent to I within its perturbated social distances space. The last ingredient of the framework is actually the more important, and is related with the evolution rules characterizing the agents' interactions. In order to develop the core of the model, we first started from the different model, as our base for the opinion dynamics. Here, the opinion of agent I at time t and 1, is given by the opinion it had at time t, plus a portion we of the difference between its opinion and that of its interactor j. In order to improve the psychological consistency of the model, we introduced in the equation of opinion dynamics either the Novak concept of agents affinity, as well as a self-consistent evolution of opinion and affinity representing a first approximation of cognitive dissonance theory. In particular, the second factor of the first equation of the model introduces the affinity between agents, indicated as alpha, as well as a cognitive dissonance-based mechanism and mathematically by means of an hyperbolic tangent. When the argument of the hyperbolic tangent is large and positive, the value assumed by the factor would tend to 1, and the portion of the difference in opinion with the interactor is covered as a single jumping counter. This is the case in which the affinity between the agents is large, to be precise greater than a given threshold alpha c, that we will describe later. When the argument of tan h is negative, the value of the factor tends to 0, so switching off the possible opinion shifting of the interactors I and j. In other words, if I hate j, it wouldn't move closer to the opinion of j. Neither if this would be very close. In other words, accordingly with the cognitive dissonance theory, the greater is the previous social connection with the source, the stronger the effect of a possible interaction with that source. Finally, the slopeness of the hyperbolic tangent is determined by the parameter beta, which control a sort of fuzziness of the system, or inertia, coupled with the first equation, determining the agent's opinion's evolution. Another equation controlling the evolution of affinity between agents is introduced in the model. In order to make the model definitely consistent with the cognitive dissonance theory, prediction is not sufficient to make the opinion evolution consistent with the affinity between agents. But it is necessary also to evolve the affinity between agents accordingly with the opinion distances characterizing the dyads. The first term of the equation just states that the affinity between two agent I and j at the time t plus 1 is basically equal to the affinity at time t. The first factor of the second term is technically speaking a logistic factor, and has just the role to bound the possible variation of alpha between 0 and 1. Moreover, this factor models also a sort of memory of the system. Finally, a second factor of the evolutionary term of the equation again introduces a hyperbolic tangent, comparing the opinion distance between the interacting agents I and j at the time t, with the critical value delta of c characterizing the system. In this case, at the contrary of the first equation, the sign of the second term can change depending on the sign of hyperbolic tangent argument, so increasing or decreasing the affinity. Basically, our model introduces 4 potential control parameters, and precisely the convergence factor mu, the fuzzy factor beta, the opinion threshold delta of c, and the affinity threshold alpha c. In order to accomplish a preliminary evaluation of the model's behavior, it's possible to consider as order parameters the number of clusters presented by the system at the equilibrium, and as control parameters the affinity threshold and the social temperature, maintaining the opinion threshold as a constant to simplify the model. And since we already know its potential role from the diffluence studies, the numerical simulation of the system produces on the left a temporal evolution of the agent's opinions, finally approaching a stable state, which corresponds to a fixed state also in the affinity matrix, as represented in figures. For what concern the second order parameter under scrutiny from our model, the social temperature indicated as kT, we confirmed how whenever this is large, and as a consequence of the perturbation of the social distances space that makes all the possible encounters as equally probable, a single final opinion cluster always tends to emerge, and a coupled saturated affinity matrix follows such condition. In this case, a trivial example of social impact theory by bilatinate can be detected, or in other words a regime where the majority appears as the final tendency of every agent seen to emerges. But when the social temperature is reduced, rich scenarios characterized by the stabilization of clusters of different sizes emerge, both in the opinion spaces, as well as in the affinity space. In general, social temperature appears to be related with the fragmentation of an opinion system at the equilibrium, or with possible metastable conditions of the system. The most important results we obtained from this model has definitely been a new numerical law explaining the fragmentation of the system at the equilibrium and the control parameters under scrutiny. In particular, a relation emerges between the logarithm of the number of clusters at the equilibrium and the logarithm of the quadratic inverse relation of the product between the critical affinity, alpha c, and the social temperature kT. The figure shows a function where first regime is characterized by the final emergence of one cluster, that through any other function approach a linear relation, in this space, between nc and the x-axis factor. Finally, the numerical approximation provided by our model is the following, and of course represents a starting point and not a final answer, even if many theoretical assumptions in classical models could be probably tested or verified. The rich phenomenology presented by the model allowed to provide a first approximation of the degree of complexity characterizing a system described by the framework. In particular, 2 evidences credit the complex system assumption. The first is related with the power law distribution, linear distribution in a log-log space as in figure, of the probability of observing a certain jump delta O by an agent. The second complexity features is related with the topological dimension characterizing the trajectories averaging determined by the model before the stable state. Using the M-box methods is possible to estimate the possible fractal dimension of a system dynamics, of course if one axis of the figure represents the time. In our case, the topological dimension of the system we created appeared to be complex, or in other words fractal. In particular, it resulted to be around 1.7, exactly between a line, a one-dimensional space that would result as 1, and a plane, a two-dimensional space that would result as 2. Actually more near to a plane than to a line. And to conclude this short presentation of the most important results provided by the model. In this figure I first report in the upper part and in the right inserted figure the quite perfect collapsing between the different functions if properly rescaled, here with the square of n, and finally, if we consider the left inserted figure, where the time required by the system reaching of the stable state within the opinion space, red, and the same variable characterizing the affinity space, black, are compared with respect to the size of the system n, on the x-axis, and with a properly rescaled measure of time on the y-axis. Of interest appears to be the crossing of the two functions in correspondence with a value between 10 and 20, as predicted by Wilfred Bion about 100 years ago, who more courageously suggested 12 as magic number for the transition between small and large group dynamics, or in other words between group and crowd dynamics. In conclusion, we developed a new sociophysics framework consistent with the cognitive dissonance theory and the psychological field theory. We provided a socio-physical core model to simulate small, as well as large group dynamics under arbitrary circumstances, and we evolved the most refined socio-physical models in literature to reach more ecological and psychologically reasonable predictions. In this way we obtained the emergence of clusters of different size, the evidence of a smooth phase transition for the community fragmentation, and a critical behavior of the system evolution. Thank you for your kind attention.